Welcome back, everyone. We're ready to start today's part of the program. We'll lead off with Seonjeong Park, who will tell us about toric varieties arising from polygon dissections.
Thank you. First of all, I'd like to thank the organizers for the invitation to this workshop. It's my honor to give a talk here. Today, I'll construct the toric varieties associated with the polygon dissections, and we'll show that these toric varieties appear as torus or closures in flag varieties. So first, I'll introduce the notion of polygon dissections, and then introduce a one-to-one correspondence between the polygon dissections and trees given by the Etherington in 1940. And then we'll construct the toric varieties associated with the polygon dissections, and then show that those toric varieties are Fano generalized bond manifold. And finally, I'll introduce that these toric varieties can be appeared as torus or closures in flag varieties. This talk is based on the following two works. Over the past 5 years, Professor Mikia Masuda and Seonjeong and I have studied on torus or closures in the flag varieties, and this is one of our joint work. And another collaborator, Jeonju, is combinatorialist. Okay. I'll start with some objects in combinatorics. So polygon dissections, we'll denote by Pn plus 2 a regular polygon with n plus 2 vertices. So there is the P10, and we'll label the vertices from 0 to n plus 1 counterclockwise, and the edge connecting 0 and n plus 1 is called the base. So I'll draw the base edge in a dotted line as in figure. Then a dissection of a polygon is obtained by drawing diagonals, where when we draw diagonals, we do not allow the intersection. So for example, this is a dissection of P10. And a triangulation of a polygon is also a dissection. And in this case, we draw n-1 diagonals. So when a dissection produces k small polygons, we call the k dissection. So this is a 4 dissection, and this is 8. Sorry, this is 8 dissection. So k varies from 1 to n, and on n dissection is a triangulation of a polygon Pn plus 2. So we denote by I, j, the edge connecting the vertices I and j in a dissection, and we always assume that I is less than j. And if there is no confusion, we simply write ij, just ij. So we have 3 diagonals in 0, 3, 0, 7, and 3, 7 in example. The number of polygon dissections are already studied in combinatorics. So the number of k dissections of the polygon Pn plus 2 is 1 over k times n minus 1 to the k minus 1 times n plus k to the k minus 1. And it is called the Kirkman-Kelly number. In particular, when k is n, the number is the same as the Catalan number Cn. And the sum of f of n comma k is known as the n plus first small Schroeder number. That means the number of all dissections of a polygon Pn plus 2 is the n plus first small Schroeder number. Note that there are two kinds of Schroeder numbers. One is a small Schroeder number, another one is a big Schroeder number. And big Schroeder number denoted by large Sn, and Sn is the number of lattice paths from the southeast corner of an n by n grid to the northeast corner. We using only single steps north, northeast, or east, and that do not rise above the SWNE diagonal. So for instance, big Schroeder number S2 is 6, and small Schroeder number S2 is 3. Okay. And a small Schroeder number also describes the number of Schroeder trees with n plus 1 leaves. And here the Schroeder number is defined as an ordered rooted tree whose non-leaf vertices have at least 2 children. So for instance, these 4 are examples of ordered rooted trees. And among these 4 trees, only these 2 trees are Schroeder trees. And as an ordered tree, these 2 are different. But they are isomorphic as an unordered tree. Okay. Before I introduce the bijection between the polygon dissections and Schroeder trees, I'll prepare some notations. So recall that a base of a polygon is the edge connecting the smallest vertex 0 and the largest vertex n plus 1. So we allow this notion, then a dissection of Pn plus 2 produces a set of small polygons whose base is the base of Pn plus 2 or a diagonal in D. So in this example, you have 4 small polygons, and this polygon has a base 0,9, and this triangle has a base 0,7, and this square has base 0,3, and this pentagon has base 3,7. And we label the small polygons in D using their bases. So for instance, in this case, this square is P of 0,3, P of 0,7, P of 0,9, and P of 3,7. And we let the set E naught of D be the set of edges of the dissection except the base. Then we can recover the dissection from the set of E0D. So for instance, in this case, we have the set E naught of D is 0,7, 0,3, 3,7 with size from 0,1 to the A9. And for simplicity, we'll denote the base 0, n plus 1 as I naught, J naught, and denote by E naught of P of I, Q, JQ, the set of edges in the small polygon, P of I, Q, JQ, except the base. Then we can see that the set E naught of D is the disjoint union of the sets E naught of P of I, Q, JQ, where Q varies from 0 to K. Okay, now I'm going to explain the Etherington's bijection. It's not difficult to see that by a figure that are drawing the Schroeder tree associated with this polygon dissections. So root is we draw the root in the center of this polygon, and we draw the edge across the 3 sides, and then we get another edge, another vertex, and then we draw this, and then we draw this. So this is the trajectory associated with the polygon dissection. And then we can find a one-to-one correspondence between the edges of a polygon dissections and the vertices of the trajectory. I mean, this root corresponds to the base 0,9, and this vertex corresponds to the side A9, this is 7A, and this is 6, 7, and 5, 6, 4, 5, 3, 4, 7, and 1, 2, 0, 1. Okay, this is 0,7, and this is 0,3. This is 3, 7. In this way, we can find a trajectory from polygon dissections, and you can also construct from a trajectory. You can also construct a polygon dissection from trajectories. So the root will be correspond to the base edge, and for the vertex, then the isolate in the pre-order listing of the tree, it will be corresponded to the I-1, I. Here, pre-order listing means the pre-order transversal, like in this way. From the root, and we first go to the leftmost leaf, and then we visit the another vertex from left to right. From the top to bottom and left to right, in this way. Then the internal vertex, whose leftmost and rightmost children are labeled by I, something and something, j, correspond to the diagonal I, j, as in the example. Okay. Then we can see that from Etherington's bijection, the base 0,n plus 1 corresponds to the root, and the diagonals correspond to the non-leaf vertices, not the root. And there's a one-to-one correspondence between the small polygons in a dissection D and the non-leaf vertices of the trajectory. And each set in other P of IQ, JQ corresponds to a set of children of the vertex IQ, JQ in PD. And there is a one-to-one correspondence between the triangulations of a polygon and the full binary root trees with n plus 1 leaves, as in example. And I'll introduce another notion of order on the, I'll give you order on the diagonals. We'll use this order when we construct the toric variety. So for a polygon dissection D with diagonals I1, J1, IK, JK, we give an order on the diagonals as follows. When I, J precedes I prime, J prime, if I is less than I prime, or I and I prime are the same, but J is greater than J prime. So in this case, 0,7 is first, second one is 0,3, and third one is 7, 9, 3, 7. Actually, this order corresponds to the pre-order listing in shoulder tree. So as we see that, so in this list, pre-order transversal is 0,9, 0,7, 0,3, and then we'll visit 0,7. So in this order, 0,7, 0,7, 0,3, and 0,7. We'll use this order when you consider toric variety. Okay. Now we'll consider toric variety from a polygon dissection. Okay. I'll just review some notions. Okay, a toric variety is an algebraic variety containing the algebraic torus lista to the n as an open dense subset, and where the action of the algebraic torus on itself extended to the whole variety. So, for instance, C to the n is a Sumtur variety, and the complex full space CPN is a projective Sumtur variety, and a generalized Baum manifold is also projective Sumtur variety. It is an iterated complex fluid space bundles. Actually, originally a Baum manifold Bat tower was introduced by the Professor A.I. Carson, and then Professor Masuda and Professor Dong-Yeop Seo generalized the notion of Bat tower to the generalized Bat tower. And when NJs are all 1, then we omit the generalized, and it's just called the Baum manifold. Yeah. Now we associate a polygon P envelope 2 with the complex full space CPN. So we first associate a polygon P envelope 2 with a polytope delta in Rn plus 1, where the sum of x1 dot xn plus 1 is n comma n plus 1 over 2, and xi is non-negative. Then we get a simplex. Then the edge vectors of delta generate the some lattice of z n plus 1. Then the dual lattice n of m can be identified with the quotient lattice of z n plus 1, 1. And if we let bar phi I be the quotient image of the sum of standard base vectors from 1 to I in n, then the vectors bar phi 1 to bar phi n is a basis of n, and by definition, bar phi naught and bar phi n plus 1 becomes zero vector. And the normal vector of delta are bar phi I minus 1 minus bar phi I. And we correspond this vector, this bar set corresponds to the side I minus 1 comma I of the polygon. So let's just see an example. We first, this pentagon will be corresponded to the 4-dimensional simplex in R5, in R4, but it is impossible to draw the the figure in R4. So we project it on R3. Then this 1, 2, 3, 4 corresponds to vertex in x1 axis, x2 axis, x3 axis, and x4 axis. And then, okay, the edge vector of this edge, the edge vector is E1 minus E2, E2 minus E3, and E1 minus E3. So the normal vector of this space is 0, 0, 1, right? 1, 1, 1, 1. 1, 1, 1, so bar phi 3. So bar phi 3 is the same as bar phi 0, bar phi 3 minus bar phi 4. And for this bar set, we have a normal vector bar phi 1 minus bar phi 2, and the triangle behind is bar phi 2 minus bar 3, and the below triangle, bottom triangle corresponds to the minus bar phi 1. Then we'll denote the bar set. This bar set is denoted by F34, and this bottom triangle corresponding to F01, and this triangle corresponds to the F12, and the backside triangle corresponding to F2. Then, so this so the original just polygon is also polygon dissections, and this polygon dissection corresponds to complex free space. And now we construct now we construct toric variety corresponding to polygon dissections. Okay, we give an order of diagonals from I1, J1, IK, JK. So for instance, if we consider this dissection and this dissection, this is a triangulation, then 0, 3, which is 0, 2 by definition. So we first note that the blowing of a smooth projected toric variety becomes also a smooth projected toric variety. So in this way, we get a toric variety from a complex projected space by iterating by an iteration of blowing ups. So we first blow up CPN along the subvariety corresponding to the base. This space, actually, this space corresponds to okay. These indices correspond to the set of the edges of E0, I1, J1. So for instance, in this case, we first blow up CPN corresponding to the subvariety which is correspond along the subvariety corresponding to the space F intersection of F01, F12, and F23. So it is this vertex. This vertex intersection of F01 and F12 and F23. So by cutting as a polygon polyton step, it is just a cutting vertex. So we get the toric variety associated with polyton. And then we'll denote this space by F03. And you can see that this polyton combinatorial equivalent to the product of a triangle and interval. And secondly, next step, we consider this diagonal. Then we blow up along the subvariety corresponding to the base, the intersection of F01 and F12. Then if we can see that the intersection of F01 and F12 is this edge. Because this is F01 and this is this is F12 and this is F01. Then if we blow up the variety, then it corresponds to the base cut of the polytope, and we get this polytope. And you can see that this polytope is combinatorial equivalent to a 3 cube. And in this way, we can define a toric variety associated with the dissection D. Then we call toric variety associated with the polygon dissection is of a Schroeder type. And when D is a triangulation, we call XD a toric variety of a Catalan type. We use this notion in the paper of, I use this notion of paper with Jeonju, and we use this name. in the paper of joint work with Professor Mikia Masuda and Eunjung. And we denote the product of PD, the product obtained from this process. Okay. So this is just example. We first cut the vertex, and then we cut the edges, and we get this simple product. Yeah. Then I show that the constructed Toric varieties become Pano generalized band manifolds. So first I will introduce the notion of Pano Toric variety. So a product variety X is Pano if the anti-canonical divisor minus Kx is ample. So for instance, complex root space is Pano, and the generalized band manifold P of C plus gamma is Pano, where gamma is the tautological line bundle over CPN. But note that not every generalized band manifold is Pano, of course. And there is a combinatorial way to determine whether a smooth projected Toric variety is Pano. I'll introduce. So for a projective fan sigma, a set of a subset R of the primitive ray vectors is called the primitive collection of the fan if the cone generated by the whole set R is not a member of the fan, but for every proper subset of R, it generates a cone in the fan sigma. So in other words, if sigma P is a normal band of a product of P, then primitive collections of the fan correspond to the minimal non-base of the product. Yeah. Non-base means every base is a intersection of some facet. Non-base means some intersection of facet is empty. Yeah. Then Bartlett gave a criterion to determine whether a project variety is Pano or not. So for a primitive collection R, then since the cone generated by R is not a member of a fan, so it becomes the zero vector, or it is in the interior of some another cone sigma. So the sum of the vectors u1 prime ul prime becomes zero vector, or it is the combination of the generators of another cone sigma, where A1 to AR are positive integers. Then from this equation is called the primitive relation. And from this relation, we define the notion of degree of a primitive collection R as the L minus A1 plus AR in this way. And a project variety X sigma is a Pano when the degree of a primitive collection is positive for every primitive collection R. Okay. And actually, the published year is published year is faster than this work, but the result was this work is the faster than this work. Anyway, so for a Toric variety XD, concept from a polygon dissection D is a Pano generalized band manifold. In particular, when a dissection is a triangulation, then it becomes a Pano band manifold. So the proof is quite simple. So if D is a polygon dissection of P and Pro 2 with diagonals I1, J1, IK, JK, that means we have K plus 1 small polygons. Then the product of PD corresponding to XD is combinatorial equivalent to the product of simplexes. Each simplex is determined by the set inert of P of IQ, JQ. So we already know that every smooth toric variety corresponding to a product of simplices is a generalized band manifold. It was proved by Professor Masuda and Professor Dongyopso and Professor Taras Panov, if I remember correctly. And so this implies, the first condition implies that XD is a generalized band manifold. And then we can also show that XD is a Fano using a Bachelef's criterion. So the proof of the first statement is the first statement is proved by the induction. So I skip the details. And for the second one, since X is a generalized band manifold, we can easily find the primitive collections. And for each primitive collections, we can easily see that the primitive relation is given by this form. So it means that the degree of primitive relation is, primitive collection is, L is the number of the size of this set. So, and the size of this set is greater than 3, always, greater than 2 always. So greater than or equal to 3. So the degree is n most 2. So it means that the toric variety XD is Fano. And the primitive relations of XD recovers the Schroeder tree TD. Because since, okay, each Uij corresponding to the vertices of a tree, and then the summation, and if it does, this relation implies that all the vertices in all the vertices in this, for every I, j, it is the children of this vertex. So it means that you can construct a Schroeder tree from this polygon this primitive relation. So using Bachelef also gave a classification result. So two smooth Fano toric variety X sigma prime, they are isomorphous varieties if and only if there is a bijection between the sets of rays of sigma and sigma prime inducing a bijection between maximal cones and primitive relations. And it means that for two toric variety XD and XD tilde for dissection D and D tilde, and they are isomorphous varieties if and only if the Schroeder trees TD and TD tilde are isomorphic as unordered Luthier trees. This is followed from this relation. And we know we can recover the Schroeder tree from this relation, and we get this result. And then you can enumerate the number of isomorphic class of toric varieties arising from dissections of P and Pro 2. And so this number is the number of isomorphic class of n-dimensional toric variety of Schroeder type. And this number corresponds to the number of isomorphic class of n-dimensional toric variety of Catalan type. I mean the toric varieties are arising from triangulations. And actually, it's not unknown the explicit formula for these numbers, but there is some generating function for these numbers in combinatorics. And we can also explicitly write the commingling of the toric variety using the Schroeder tree, but I think that I have not many times, so I just skip this slide and just show some example. Like for this example, you have 4 generators corresponding to these 4 vertices, and you have this kind of relation. All of them are written from the Schroeder trees. And Jason and I can show, I could show that if K is less than or equal to 3, and two toric varieties XD and XD prime are isomorphic as varieties if and only if their integral coordinate rings are isomorphic as graded rings. But I believe that this statement holds for every polygon dissection of a polygon, but I couldn't show yet. I believe this is true. And now I'll introduce the relation with torus orbit closures in flag varieties. So flag variety is a space consisting of all sequence of this form. This is called a flag. And if B is the set of upper triangular matrix in the general linear group, then flag variety FL sub n is the homogeneous space general linear group of C mod B. And if we let S n be the set of all permutations on the integers 1 to n, then for each permutation W, we get some permutation matrix. And the general linear group, we have a cell decomposition of a flag variety called the Broad decomposition. Like the flag variety is a disjoint union of the cells BWB mod B. And this BWB mod B is called a Schubert variety, Schubert cell, and it is isomorphic to the C to the L of W. Here, L of W is the number of inversions of a permutation W. And the dimension of the flag variety is n times n minus 1 over 2. Then, if we take the set of diagonal matrix in the general linear group, then this T is isomorphic to the algebraic torus C star to the n. And by the left multiplication, we have a torus section on the flag variety. And the torus fixed point set is the set of the permutation flags, I mean WB, where WB is this kind of flag. So there is a one-to-one correspondence between the torus fixed point set of the flag variety and the permutation group. Then there is a moment map view from the flag variety to the space Rn, where the point XB sends to this point in Rn. Here, Pi is the spherical coordinate of X, and for the permutation flag WB, mu of WB becomes the W inverse of 1, the W inverse of n. But please note that we use the different sign convention to the Tolman's talk, so we have no minus sign in this part. Then for each function W, we define the Schubert cell as the closure of the Schubert cell BWB mod B. And when V is less than or equal to W in Bruer order, we define the Richardson variety XVW as the intersection of W naught, XW naught V, and XW. Here W naught is the longest permutation. It means n, n minus 1, dot, 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 1. Then this Richardson variety is a T invariant subvariety of the full flag variety, and we say that Richardson variety XVW is toric if there is a point X in the variety such that the closure of the orbit Tx is the same as the Richardson variety. So the Richardson variety becomes a toric variety, we call it a toric Richardson variety. And the torus fixed point of XVW of the torus fixed point set is the set of permutation flags. Here Z is between the V and W in Bruer order. And its moment polytope is the convexor of this point. But of course, not every Richardson variety is toric, but some of Richardson varieties are toric. and Eunjang and Professor Masuda, we showed that if we assume V and W are of this form, then the Richardson variety XV inverse W inverse is a toric variety arising from a triangulation, and all toric variety of triangulations are appeared as a torus orbit closure in appeared as a Richardson variety X of this form. So there's one bijective correspondence between the there is some correspondence between the Toric Richardson variety and the set of unorderable binary trees with n+1 leaves. So we can naturally ask that, can you realize a toric variety arising from a polygon dissections as a torus orbit closure in a partial flag variety? So partial flag variety is a sequence of this form. So we ignore some subspace in the full flag. So there is a natural projection from the full flag variety to the partial flag variety by ignoring several subspace Vi. Then this is the theorem of Gelfand-Servanova, but since we use the different sign convention, so we can show that for every point X in this partial flag variety, the moment map image of the torus orbit closure Tx is the mean sum of the polytope, this polytope. And actually, this delta mi is determined by the list of X. It is the corresponding to the non-zero critical coordinate. And then we can see that the toric variety XD from a polygon dissection becomes a torus orbit closure in FLN to the K1.Km. Here Ki is the number of leaves of depth I minus less than or equal to I minus 1 plus the number of non-leaf vertices of depth I minus 1 in the shred tree. And moreover, this XD, actually, this is the image of a toric variety of Catalan type via the natural projection. So for instance, we can prove that there is a point X such that the band of the torus orbit closure is the same as that of XD. And for instance, if we see this example, then K1 is the number of vertices of depth 0. So there is only one root. So K1 is always 1. And for K2, the number of leaves of depth less than or equal to 1 is 7, 8, and 8, 9. So 2 plus the number of non-leaf vertical depths 1 is 0, 7. So K2 is 3. And for K3, we have these two leaves and these two non-leaf vertices. So K3 is 4. And the last Km is always the number. And so if we see this example, then this one M1 corresponding to the set of the integers from 0 to 9. So it corresponds to the leaves of the shred tree. And next step, we consider the critical coordinate corresponding to I, A, 9. Here I varies from, so this is 7. This is a type of 7 from 1, 2, 3, 4, 5, 6, 7. And next, K3 corresponding to the critical coordinate I, J, A, 9, where I is 1 over 2 or 3, and J is 4 over 5 or 6 or 7. In this way, you can find the list of a point X. And if we consider the canonical triangulation of a polygon dissection in the example, then we can realize that the toric variety XD is a projection image of the toric Richardson variety X beam double inverse in the full flow FL line. Here V is this number, W is this number. We can find this the form of V and W from the full binary trees. There is a way, but I just I think there's no time. And I like to explain one problem. So we see that today we see the toric varieties arising from polygon dissections, and they are Fano-Gerard manifolds, and they appear as a torus-orbit closures in partial flag varieties as a projection of the toric smooth Richardson varieties. So we already knew that these four, this part, and these four parts are non-empty. We already know that, but we do not know these two parts, they are empty or not. Okay, thank you for your attention.